What's up, guys? Hello, guys. Okay, in the previous video, I gave you kind of a demonstration or explanation, if you will, of how the moment distribution works. Now we're gonna be working with some definitions and assumptions that you have to be paying attention. Remember this method, the first thing, and we mentioned it before, it only takes into account the bending deformations. Important. It's a displacement method. We already discussed that. It was devised by Hardy Cross in 1924ish or something like that. And and here we are. So let's talk about the definitions first. Definitions and assumptions, conventions. Let's say conventions first. And then we're gonna go about the assumptions later. Conventions. Okay, nice. First, depending on the textbook that you are using, these definitions and conventions, the conventions especially changes. But for my approach, the approach that I'm going to be following, we're going to consider counterclockwise. We're going to say that is positive for enforced members, for end forces, meaning this is going to be positive, and this is what we have been doing all the time. But clockwise is going to be positive for externally concentrated applied moments. And this is also, we have been discussing this all the time, especially when we do free body diagrams, and I say, oh, if this is like that, remember, complete it, go to this side, and look at the way this points up. So this is what I'm trying to tell you. This is going to be positive only for external concentrated moments. Now, the other thing that we have to talk about is the member stiffness, bending stiffness, of course. Member stiffness. Now, the member stiffness you can derive, can be derived, by conjugate beam, but in this case, I'm gonna be using slope deflection because it's a method that we discussed before. And basically, we did that before, but I'm just gonna refresh you really quick. I know that, by the way, if you guys are not really into definitions and really into assumptions and conventions, which I strongly suggest you to be, at least at this level, because then you're gonna know what is happening. Just go to the end of the video. I'm gonna show this table at the end of the video, and in this table is everything that you need to know. But anyway, so this is what we have, and we discussed that if we apply a moment here, or it's gonna produce a rotation here. If you call this A and this is B, the rotation at B is 0. The far end is fixed. So if we use that and we apply a slope deflection, then you know that A and B is gonna be 2EI divided by L. 2EI divided by L multiplied by 2 times rotation at A, which in this case exists, plus rotation at B, which is 0, plus the rotation minus 3 times the rotation of the chord, which is also 0 because it's not rotating, plus the fixed end moment at AB, which is 0 because this is just, there's nothing here in this part. So basically the moment AB is going to be equal to 2 times 2, 4 EI over L, rotation at A. Now the member stiffness is the term bending or rotational member stiffness is defined as the moment that that is produced to achieve a rotation of 1 radian. So in other words, if you put 1 radian here, this is the member stiffness here. So the moment is going to be equal to the bending stiffness or the member, and it's 4 EI over L. That's what we are looking for, okay? This part. Now, no, the far end, I'm gonna work it now, but I'm gonna work it with the modified equation when the far end is a hinge. So let's say that I have this and I have this now here, and I do the same thing, and I apply the moment here, and this is gonna produce a rotation here, but it's gonna produce a rotation there also in the other end, in this part here, and this is the rotation. If you use the modified equation for a slope deflection that we have, then we once again, this is A and this is B, but now the far end is hinge. Then you're gonna have that moment AB is gonna be 3EI over L, this is the formula, times rotation at A minus the rotation of the chord, which is 0, plus the fixed end moment AB minus the fixed end moment BA divided by 2, which are 0 and 0 in this case. So the modified expression gives you this value. If you make the rotation 1, the K is going to give you 3EI over L. That's the value for K for the far end, when the far end is a hinge. Now, relative bending stiffness, that's another concept. Relative bending stiffness, that's called K, not K bar, but K. Basically what this is another value that we use, and if it's the same material, so if E is constant, this K is obtained by getting the absolute stiffness, member stiffness, and divided by 4E. That's basically what we do. In other words, if we do it that for this case, and we divide that by 4E, then my small k is going to be equal to 4EI over L over 4E. This and this cancel each other out, and this means that the K is going to be equal to I over L for a far end fixed. Now if the far end is pinned, K equals, this is the formula, right? 3EI over L, 3EI over L divided by 4E. This and this cancel out, so that means that K is going to be equal to 3/4 of I divided by L, and this is for far end hinge or pin. Good. There's another assumption here for the relative bending stiffness, and the relative bending stiffness also, if the beam is symmetric, for symmetric beams, in geometry and loading, and I'm not gonna do that derivation, but it's simple, right? If you just go half of the length, then what is gonna happen is K is gonna be half of that value, I over 2L. And if you have symmetric beams, symmetric geometry with anti-symmetric loading, then K is going to be equal to 3/2 of L. That's basically it. Now, what else? We have also, this is page number 2. Now, there's another thing that is called carry carryover moment. And this carryover moment, if you remember the definition, the introduction to the definition when we were doing this, the carryover moment is how much moment is going from here to there. That's the carryover moment. So the carryover moment is gonna be, and we can calculate that also by using, or we can demonstrate that by using slope deflection. And it was something like this. So if we have this and we have this moment here, moment AB producing this rotation here, then we could, this is A and this is B. We calculated that A, right? So if we calculated that B, here it's going to be 2EI over L multiplied by rotation at A plus 2 rotation at B minus this plus the fixed moments. Fixed moment AB minus fixed moment BA divided, no, BA here and AB divided by 2. It doesn't matter, this is 0 and this is 0 and this is 0 also, but this is not 0. So the moment BA is going to be equal to 2EI over L rotation at A. But if you remember, the moment AB, when we calculated, it was, I'm looking for my papers, that could be a song. Looking for my papers. It was this one, 4EI over L. 4EI over L, meaning that was 4EI over L rotation at A. So by producing this moment here, look what happened. I transfer the effect of this to BA and it's half of that. So basically the carryover factor is going to be 0.5 if the far end is fixed, but the carryover factor is going to be 0 for far end pin, because there's nothing. I mean, if I go from this end to the other end, that's going to be 0. Okay? Good. 3. Keep going. I want to finish this so we can start doing problems. Problems. 3. Distribution factor. Which is DF. Distribution factors. Where is my definition? Here, distribution factors. When we were explaining this in the previous video, I was telling you, once you find this unbalancing moment, this balancing moment has to be distributed between these two elements, between this element and this element. How are you going to distribute that? You're going to distribute that based on the distribution factors. That's what you do. And these distribution factors are based on no other thing than the stiffness, the bending stiffness of the element. So basically the distribution factor, what it's telling you is how much of the moment, of the balancing moment, of course, balancing moment is absorbed by each member connected to the joint. And of course, it depends on the bending stiffness K or K, which is the same. Now, so let's say that you have, now let's go a little bit more complicated. Let's say that you have something like this. And then this is A, this is B, this is C, and this is D. And this thing is gonna deform depending on the load, the weight of the load. It's gonna deform something like this, I don't know. something like that, maybe like that, something like that, I don't know. And then you have these distances, and this is L2, this is L1, L1, L3, and then you have also an inertia 2, inertia 1, inertia 3. So with each one of these values, then you can calculate different K. So you can calculate K1 here, or KAB. Yeah, I should call this, well, K1, you get my point, right? K1 is the K of these in this element. So what is that? I1 divided by L1. Why? Because the far end is fixed. Now if you go to here, we just say that the far end is a pin. So if the far end is pin, that K, small k, the relative one, you can use also the absolute one, but the relative one is going to be 3/4 of I2 over L2, and this one here, the far end is fixed, so this is going to be K is going to be equal, this is K2, this is K3, it's going to be equal to I3 divided by L3. So then the summation of all the K's is going to give me the total stiffness of that joint. If I want to know how much of this moment that I'm going to put here somewhere is going to be distributed here on each one of them, then you can calculate the distribution factor for BA will be K1, how much stiff is this compared with the total stiffness of the joint. That will be the distribution factor. The distribution factor of BD is how much stiff is this, what is the value of the stiffness of this if you compare it with the total stiffness of the joint. And the distribution factor of BC is how stiff is the member BC compared with the joint. That's basically it. We haven't talked about stiffness factor AB or DB or CB, but I'm gonna calculate those also here, so you don't have any concern, any doubt. Let's say that I want to calculate the distribution factor for AB. Distribution factor for AB will be the summation of the value of the K for AB, which is K1, divided by the stiffness of that joint. The stiffness of that joint is this stiffness, K1, plus the stiffness of the fixed support, which is infinite. So basically what we are doing here is K1 divided by infinite, and K1 divided by infinite is 0. Meaning every time that you find a fixed support, the distribution factor for the fixed support is going to be 0. And if you talk, so this one is going to be also the distribution factor for CB. Now if we want to calculate the distribution factor for DB, which is pin support, then it's going to be what? It's going to be this value, which is K2, divided by the summation of the stiffness of that joint. How much is the summation of the stiffness for that joint? It's just K2, that's it, there's nothing else there. So this is going to be 1. So whenever you have a pin support, or even, look, even if you have a pin support, or you have a roller with a cantilever, so let's say that you have something like that. If you have this type of situation, like I'm showing now, or you have the same situation that you have there, let's say that you have, let me keep going with the same example. Let's say that you have something like that. This could be a roller, this could be a pin, this could be whatever, but you have that. And then I want to calculate the stiffness of this member. The stiffness of this member, whenever you have a cantilever part, that cantilever part do not add to the stiffness, because there's nothing, this is just hanging there. It can add the moment, yes. It can add a shear, yes. But stiffness, it doesn't add anything. So if you have a cantilever or you have something that ends in a pin or in a roller, the distribution factor for that one is 0. So those are all the things. The other part is the fixed end moments. The fixed moments are these. The values, assuming that everything is locked. Those are the fixed end moments. And the fixed end moments, you can calculate them using slope deflections. You can calculate them using conjugate beam, I don't know. Or you can read them from tables, you see? You can see this part, let me out of focus a little bit. Well, a little bit. But if you can get this from anything, okay, from anywhere, from any book. Any book has this type of tables. Maybe it doesn't have such comprehensive like this one, because I put every single case, but you can find them. I'm pretty sure that you can find them if you look for them. So this is the table for fixed end moments that you find in the inner cover of the back of the books. Usually you can find them there. So that's it. We have a video on how moment distribution works, and then you have another video on all the assumptions that we use when I don't think I'm missing anything. Let me take a quick look just in case I'm missing something. No, I'm not missing anything. Arrivederci Roma. I see you in next video. Be good, behave, stay safe. Bye.